some early architecture assumptions begin to reach their limits, and that's question four. Why has the transition to IPv6 taken so long? And what does this tell us about large-scale technological change?
The entire internet's computing revolution has actually ridden a more fundamental revolution in silicon chip manufacturing technology, which we often call Moore's Law. That since the original invention of the integrated circuit in the late 1950s, engineers building these integrated circuit fabrication plants have been able to double the number of gates on a silicon chip at the same cost per chip every 2 years. So what's actually happened is every 2 years, computing got twice as fast, but cost per unit of computing less than half every 2 years. So what was going on was that the computers were getting more powerful and cheaper and smaller, and they were getting more prevalent. Now, this is the precise opposite of the technology model of the predecessor of the internet, the telephone network, which had very, very simple, dumb devices, a speaker and a microphone, and all the intelligence was placed into the network. So the network actually carried the money, it carried the importance, it carried all this weight of investment, and the edge devices were basically useless appendages. Once you get a huge amount of computing capacity attached to the edge of the network, they have more processing capability than the network could ever dream of. There are millions, hundreds of millions of computers and one network. And so all of a sudden, you can do a whole lot of work at the edge you didn't need to do in the middle. Now, the first designs of the internet were, I think, strongly influenced by a telephone-based model of connectivity and technology, that the network was still trying to do a fair deal of work, and it was trying to relieve the processing power on end systems. It was trying to make the connected computers relatively simple. And so the whole idea of an address-based network, where every device had a consistent and permanent address, was, I think, a throwback to mainframe thinking of the 1970s. When we really started to scale up scale up technology, we very quickly realized that the most scalable model was to actually make the network asymmetric, different. There were servers and there were clients. At home, at work, people had clients. My mobile phone is a client. My watch is a client. It doesn't serve, it actually uses services. Now, a client doesn't need its own address permanently. I don't need to get in touch with a client. Clients get in touch with servers. And when you look at the network from that perspective of client-server architectures, you very quickly realize that addresses are not the fundamental language of a network, not anymore. Addresses are merely temporal tokens to stop packets getting confused. So all I've got to do when I want to make a conversation as a client is borrow a unique address, use it for the length of my transaction, and then throw it back in the pool, because after I've used it, I have no further need. And we've actually subtly changed the internet without even noticing it into a network that is actually based on a naming system. It's domain names that matter. Now, scaling addresses is hard. Unique addressing is hard. Scaling that to 30, 40, 100 billion devices, a trillion devices, is a nightmare. No matter how you try and do it, it's expensive. Let's not bother. Let's just walk away from all of that and instead name the servers. Not give them addresses, but name them. So names are important these days for scaling. Addresses are just a convenience at a network level. They don't actually need to be unique. They're quite ephemeral in some ways. And that has been the key to almost unconsciously building a network that handles 30 to 50 billion connected devices today, and we're confident we can grow that tenfold or even 100-fold without changing the fundamental architecture. So that was the big key. We're using the power at the edge, not trying to scale the middle.